Welcome back. Here we go with session 12, part 2, beams 2. In our last part of this session 12, we discussed how we could create bending moment and shear force diagrams along a beam using equilibrium. We're now going to discuss another approach to constructing shear and bending moment diagrams. And this approach is based on relationships that we derived in our last session, session 11. Relationships between distributed loads and shear forces and shear forces and bending moments. So the two equations that are most relevant here are dv dx equals wx and dm dx equals v of x. Using these equations, we can adopt a methodology as described by Hibbeler in his book. And this methodology has two primary steps. The first step is to do essentially external equilibrium. So calculate the external loads first, and then we're going to calculate the shear forces at the ends of the beam. Now this means taking that reaction force at, say, one end of the beam and another end of the beam, and just going slightly inside the beam to look at what the internal shear force is related to that external shear force or external loads that are acting on it. We do the same thing with the bending moments as well. And then we calculate out what the internal bending moments are at the ends of the beam. Step 2 is to use the differential or integral forms of the shear force relationship to create a shear diagram, or the differential or integral forms of the shear force bending moment relationship to calculate and create a moment diagram. Now, in just a few minutes, we'll go through how to use this methodology. But before we do that, I want to show the same example we did last time in a couple of different lights, primarily looking at the use of both the differential form and the integral form of these shear force, bending moment, distributed load, shear force relationships. So let's take a look and say we have some relationship between the slope of the shear force, V, as a function of x in terms of the distributed load, right? That's just putting into words what this equation is. So dv dx is equal to w of x. Similarly, we have a relationship between the slope of the moment, m, as a function of x, and that being equal to a shear force. So if we were given, for example, a bending moment, we could take the derivative and then calculate the shear force. With the shear force, we can take a derivative of it and calculate the distributive force. Now, this is not the normal way of operating. What do I mean by that? Well, let's take a look at this curve that we have for the bending moment as a function of x. This may look familiar because we've seen it previously, but it doesn't tell us immediately what the beam looks like or what the transverse loading on the beam might be. Okay? But maybe we can get there, and we can, by using these equations. So we say, hey, take the derivative of this moment, which is of a quadratic form, to figure out what the shear force is. So just graphically at this point, we know this is a second order system. It has some negative coefficient times an x squared, and maybe some other terms. So if we take a derivative of that, it's going to go from a second order quadratic equation to a first order linear equation. And we've said that it looks like it has some type of negative coefficient times maybe an x squared. So what do we expect? If we take the first derivative, we're going to have some type of negative coefficient times x, which would be a negative slope, which would be something like what we see being drawn here. So we might go from some value having a negative slope, okay, between 0 and L. Similarly, we can take the derivative of this expression to get the distributed force. And when we do that, what do we see? Well, this is a first order equation, and so some type of negative coefficient times x. And in fact, we know what that is. Say the rise is minus W naught L, and the run is L, so it's going to be minus W naught. And we take the derivative. What do we get? We get minus W naught here. Okay? So we're able to use these equations in their differential form to go from bending moment to shear force to distributed force. And even though that may not be the direction that we go, they offer a nice form to check that what we have created makes sense. So if the differential forms take us kind of from the bottom up, the integral forms, they can take us from the top down. dv dx equals wx. We move the dx to the right side, and we get dv equals wx dx. If we take the integral of wx dx, we can say integral, some indefinite integral would have been plus a c, or c1 or c2, whatever we define as our constant. And we confirm that integral. A definite integral form, we could say, hey, we're going from some a to b, and we had some value for shear force at A, and we have some value at shear force at B. And we can look at VB minus VA as kind of this delta V between those two, and we can write the equation of this form, in this form. So now what we're saying is if we have a distributed force, we can integrate to get the shear force. And that kind of looks more familiar in terms of, well, here's a problem that might have a distributed load on a beam. Let's figure out what the shear force is. Similarly, we remember that dm dx is equal to v. And if we rewrite that equation, we get that dm is equal to vx dx. So moving that dx to the right side. Once again, we look at integrating from some a to b. We have some constant we have if we were to have an indefinite integral. And we can write that delta m is equal to integral vx dx. So what does this mean? It means that if we have the shear force, we can integrate to get bending moment. So let's start with this familiar problem. We have a distributed load on a cantilevered beam, and it has a constant negative W naught. Okay, so if it's going down, we typically define that distributed force as being negative, but its magnitude is still W naught. So if we want to use the integral form, we can say, okay, integrate this Wx, which is equal to minus W naught, across the beam. It's going from 0 to, say, L. And this is 0th order, which means we integrate, it's going to become first order. And it's got a negative W naught for its slope. And when we integrate, that's what we see. This is just using graphical methods at this point, or we're just plotting, okay, without doing all the algebra. We're going to do all the algebra in just a second. If we want to go from this first order equation to the bending moment, okay, so if we go from shear force to the bending moment, we can integrate. When we do that, what do we get? We get a quadratic, and it has this familiar form. Okay, so this technique is useful for being able to plot or have an idea of what the corresponding shear force would be for a beam with a distributed load on it, and what the corresponding bending moment would be for the internal shear force acting across a beam. So let's now more formally use the methodology. We have now a kind of a qualitative sense of how these differential and integral forms of these two equations can help guide us in making these plots or understanding these plots or checking these plots. Let's now use this methodology with exactness. Start with our distributed load acting on this cantilever beam. And our first step is to calculate the external loading. So we'll do external, we'll perform our calculations associated with external equilibrium. And to do that, we'll redraw the beam with reaction force and reaction moment on the left side. And we'll call the reaction moment MA, we'll call the reaction force R. We'll also simplify our distributed force and say that it's some effective force acting at L over 2, and it has magnitude of W naught L. Now, this effective force is pointing downward. Okay? So we should be a little bit careful that we keep track of things appropriately. It's perfectly fine here, though. Okay, we've kept the arrow down. This is going down, and this is external equilibrium. So we don't need to be as concerned. We should still be concerned that positive is positive and negative is negative, but we don't have to be as concerned with our conventions. We can say that the external reaction moment is counteracting this effective force acting at L over 2, as we see here. And we can say that the reaction force is balancing out F effective. So it's W naught L, as we see there. What if we want to do some additional work in following our step 2? Okay, that was wordy. Let's just go to step 2. So to do that, I'm going to clear out a little bit of space. So I disappear for a second. And we begin to look at the differential, or we begin to look at the shear forces and at the ends of the beam and the bending moments at the ends of the beam. So let's look at values at the left end. What we do is we draw out just a little bit of a sliver just to the right of A. And it's such a small sliver that there's no contribution from W naught. Okay? Because let's say that you have W naught acting over a very small delta X. That's going to end up being 0. So we don't have a contribution from W naught, at least not an effective one. And we have RMA that we calculated previously. We draw internal shear force V and bending moment M. V of 0 is going to be equal to R. Okay, that's how these two balance out with each other. Second law. M of 0, okay, is going to be, okay, so this is the M. It's going in the same direction as MA. So that's going to be just the negative of whatever MA is, and that's W naught L squared over 2. So minus W naught L squared over 2. At the right side, okay, so we're over here now, what do we have? Well, if we draw a sliver, we again say that W naught's making negligible contribution at the right end, and that means that V there has to be equal to 0 because there's nothing acting downward or upward externally on this system. This is a free end on the right. And M is also going to be 0. There's no moment being applied here. So we've now written that the shear force and the bending moment are these values on the right side. Let's move to step 2. We're going to use differential or integral forms of distributed load shear force relationship. Well, in this case, we probably want to use the integral form. So we're going to do some type of integration to create this shear force diagram. And what are we integrating? Well, we're integrating, if you recall, we're integrating W. In this case, let's be a little bit careful. W is equal to minus W naught. Okay, so the integral that we're going to perform is as follows: integration of minus W naught dx. We go one step further, we perform that, we have the minus W naught x plus a C1, okay? And now is probably a good time to use a boundary condition. So we have two choices. We could plug in that we're going to have V of L at the right side equal to 0, or we can plug in V of 0 is equal to R, or W naught L. It's probably simpler to say substitute in 0 here and see that C1 has to be equal to this W naught L. So we see V of 0 is equal to W naught L, and that means that C1 has to be equal to W naught L. When we do the plot, what do we see? We see, well, okay, we've now, I mean, a couple ways to look at this. One, you could say, oh, it's just a linear equation, right, with the slope negative W naught, and I know where it starts, W naught L, and I know where it ends at 0, okay? Or you can say, okay, well, I've got this nice first order equation, and I can then do the plot based on the y-intercept being W naught L, and the slope is minus W naught. Either way. Let's go further and use the integral form for the shear force bending moment relationship and create the moment diagram. So here's the diagram, unpopulated at this point. And what we'll say is that the moment is got to be equal to an integral of the shear force dx. Well, what is the shear force? Well, the shear force, actually, we have an expression now, right? It's minus W naught x plus W naught L. So we can do the integration, or we can do substitution and then perform integration here. And this is going to give us minus W naught x squared over 2 plus W naught Lx plus another constant. What do we do to figure out this constant? Well, we, again, choose a boundary condition. So let's go with the moment at 0. So the moment at here, what is it equal to? Well, we calculated it out as minus W naught L squared over 2. Well, this is going to be 0. This is going to be 0 when I plug in 0. So what does C2 need to be? It needs to be this minus W naught L squared over 2. So that's what you have here. C2 is minus W naught L squared over 2. When we go ahead and we plot, we could, again, probably put in 2 points, right? We know what's happening at 0. We know what's happening at L. It starts at minus W naught L squared over 2, and it goes to 0. So we could plot a point here and a point here, and know that it's a negative quadratic, okay, and do that plot that way. Or we could use this whole equation and attempt to figure out what it looks like by following, finding the when this is equal to 0. It turns out it's over here, but it's probably better to use a combination of our intuition and boundary conditions with knowing that this is a quadratic, okay? And this is the formula you get, and this is familiar, right? So we still use equilibrium on the external end. We still use equilibrium to figure out the shear force and bending moment at the ends, just adjacent to the constraints, but we didn't do integration or method of sections as we've done typically. Instead, we use integration with these 2 equations to be able to create these plots. So now it's your turn. Go ahead, take some time, start by creating this problem as you see here, as we see here, and begin to use the methodology. And as we do this question, keep in mind a couple of things. One, we can perform external equilibrium, and we can think of this W naught as being acting at the middle, having magnitude W naught L, okay, like that. And we can also take advantage of symmetry, which allows us to state that this reaction force to the left is going to be equal to the reaction force to the right. So take some minutes of time to perform this exercise, and I'll see you at the next session or next part of this session. Thank you.